Okay. Okay, guys, welcome to our last lecture of this term. We're here. We made it. It's almost December. We started in August, so hey. I still remember the first lecture, we had 87 people. So you guys have made it, and I remember sticking around, and we had maybe 40 people sticker. It was bad, so I I knew that wasn't gonna last. So that's okay. That's good. Uh, Paper topics are due tonight. I hope people remember that. Uh, I highly encourage you to try the paper and try the presentation. Highly encourage it. Even if you don't know exactly what topic you want to do, it's okay. You don't have to have a perfect topic written down. I think last time 4 people wrote papers, and I think 2 or 3 of them we went back and forth for a little bit talking about ways to adjust it. So, and I remember for the first paper, I did spend some time talking to you guys after class and stuff. So if you want to do that, that's fine with me too. Or come tomorrow morning if you want to discuss your paper. That's what those Sunday mornings are for. Uh, Yeah, so then after I get everyone's topics, I will send out an email to those people just outlining sort of the procedure for next week and the week after. So today's Gabe's final problem solving session before January. Whew, it's crazy. It will be on the problem set on special relativity, which I posted last week. As you guys saw, it was nothing crazy. It was just some 4-vector stuff, and there's a nice matrix problem in there, which would be nice for you guys to see. So he'll do that. And today we're going to start QFT. Now, the title of this was the conceptual basis of QFT. Quantum field theory is a very beautiful subject. I think it's the most beautiful subject created by mankind. And I actually mean that because it's one of those things where it's one of those triumphant feats, right, of humanity. It's like when humans went to the moon or built the Great Pyramids, or there are these triumphant feats of humanity. Quantum field theory is definitely one of those. I mean, first of all, the historical way it was developed is just incredible. That's the first thing, and I encourage all of you to read about it. The second thing is you have to understand you had the smartest people on earth working on this thing, developing it. I mean, all of the crazy scientists were put in Los Alamos trying to develop the nuclear bomb. And at the same time they're trying to develop the nuclear bomb, they're coming up with the standard model and QFT and quantum electrodynamics. So it was a really crazy time for theoretical physics. It is a very mathematical subject. It is very technical. It is it's difficult. It's not easy. Uh, I remember I was signing up to take QFT1 last year as a junior. And usually you take it in grad school, but a lot of undergrads take it too. And I went to the professor, you had to get permission to take it. And the first thing he says to me is quantum field theory is a full-time job. And he said that to me. And obviously, as an undergrad, you have many other commitments, right? You're not just taking classes, you're doing clubs, you're doing this, you're doing that. So as an undergrad, but that's what he said. And I totally understand what he was saying because the reality is you need to put in the time. You have to do your reading. You have to really do as much outside work. And even then, usually they say it takes another pass to really understand what's going on. So, yeah. I have a lot of textbook recommendations. I'm not going to do that today because we didn't start. When we start QFT in January, then I will do that. I think the first class for about half an hour, I'll just show you all the textbooks and I'll tell you which ones are good because it is so important to use outside sources because I'm not using a textbook. So for quantum mechanics, I had a mix. 90% of the time I did not use a book. Sometimes I did for some topics, which I was a little rusty on. But this is not something I'll use a book for. So you should really use other books. My lectures are not enough because I'm not a master yet. Uh, Yeah, so I'm going to give you a tourist's tour of what is field theory, why do we need it, and it will be mathematical today. A lot of it is not going to make a lot of sense. You're going to be like, where did he get that? What's that? What is that? That's okay. It's a tourist tour for a reason, right? We're not going in depth with each derivation today. When I actually do teach you guys QFT, I'm going to focus on doing a lot of problems actually, because I think that most of the time people don't do problems in when they teach quantum field theory, and that's good to see. So, anyways, let's begin. Let's talk about QFT. First of all, why do we need QFT? I think we should spend a minute and talk about that conceptually. So why do we need QFT? What is the purpose of quantum field theory? Why does quantum mechanics fail, right? So the whole point of quantum field theory is very simple. We want to create a quantum theory that is unified with special relativity. That's the whole purpose of quantum field theory. So quantum field theory is a unified theory of special relativity in quantum mechanics. Okay? There are many consequences of adding relativity, special relativity, into the mix. The first consequence is this idea of multi-particle states. So as you increase energy in any regime, or if you try to localize a particle, the more you try to localize it, right, the more energy you're going to create because of the uncertainty principle. At a certain point, you will create new particles because the energy will get so high that that one particle will turn into multi-particles. In quantum mechanics, we don't know how to deal with multi-particle states, right? We have one wave function and that's it. And we work with that wave function. That's the first reason. The second reason, as you'll see, and I said this last class for special relativity, we want our equations in general in physics to be Lorentz invariant, right? We're going to do a deep dive into what Lorentz invariance means today. I'm going to really show you what Lorentz invariance means. It really means that under Lorenz transformations from frame to frame, our equations stay the same. I mean, that's crucial, right? Because if your physics is not the same from one person to the other, I mean, what are you even doing? And turns out the Schrodinger equation is not Lorenz invariant. Okay, so that's a problem, right? So there are multiple reasons. Now, it's very funny because the first equation I'm going to show you, our first relativistic wave equation, right? Because that's what field theory equations are, relativistic wave equations, was discovered by Schrodinger actually, and Schrodinger threw it out. And then he came up with the Schrodinger equation. So there was really no motivation for a relativistic theory of quantum fields until a little bit after. Yeah, so there was, it was sort of by accident. Now, usually in physics, the mathematicians invent the math first before the physicists come along. Quantum field theory is unique. All of the math and all of the ideas, the abstractions were created by physicists because there were real physics reasons. So this is actually a theory that is really studied by all kinds of mathematicians. I mean, to be honest, the actual formalism of quantum field theory, if the axioms of quantum field theory are not really defined. In fact, there are these problems called the Millennium Prize problems in mathematics, pure mathematics. And if you solve them, you get $5 million. They're out there. 3 of them have to do with quantum field theory. And there's 6 Millennium Prize problems. So, and that goes to show you that the real foundational underpinnings are not solid because physicists invented it. So we skipped all of that. So for example, we're going to learn that the basis of, you guys all know what the standard model is, right? You've heard of that? Okay, right. The standard model is this whole picture of elementary particles and interactions. That's what we're going to try and describe. That's what we're building towards, learning about the standard model. You guys have all probably seen that the standard model fits on a t-shirt, right? Okay, that's like a famous thing. So yeah, so we're going to learn what all of that is. That's the whole idea. Now, standard model is a kind of theory called a non-abelian gauge theory. Okay, you will learn what that is. Moreover, it's really called a Yang-Mills theory. And the mathematical foundations of these Yang-Mills theories are very, very shaky. To physicists, it doesn't matter, but I'm just trying to get you guys to think about how rich this subject is. If you want to write a paper about what we do today, I'm not opposed to it. So something to think about. Okay, let's begin. So that's why we need quantum field theory. Please stop me if you have questions. Okay, so let's begin. So let's just start with our normal Schrodinger equation. This is our normal Schrodinger equation, right? It's standard. It's basically tells us about all the dynamics in quantum mechanics, right? A good old Schrodinger. Now, if I have a free particle, my Hamiltonian is just p squared over 2m, right? Where p squared is an operator, right? Right. So p hat, again, this is all review. P hat is just h bar over I nabla, right? In 3 directions. Stop me if any of this is confusing. Please, 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 because it's going to get very complicated. So if we're not on the same page. So remember, this is the gradient operator, del x, del y, del z, right? Okay. So if I plug in this Hamiltonian into my Schrodinger equation, it becomes the following. In position space now, right? Psi of x and t equals minus h bar squared over 2m nabla squared psi of x and t, okay? That's our standard Schrodinger equation for the free particle, which we've solved many, many times, right? Now, if I asked you guys, okay, let's come up with a relativistic Schrodinger equation. That's the goal. The most natural thing to do would be to say, let's start with the relativistic energy, right? Because the Hamiltonian's an energy, right? So let's just start with the relativistic energy and plug it in. That would be the natural thing to do, and that's what people did. That's what they first did. Instead, let's just start with the relativistic energy. Let's plug it in. I see you have something excited about that. Let's plug it in, and let's see what happens. Relativistic energy squared, p hat squared c squared plus m squared c to the 4th. So that's the special relativistic energy, right? Yeah. And so the whole idea would be to plug this into the Schrodinger equation. So let's try that. So we plug that in, and we get IH bar del t. I'm going to drop the t's because I'm tired of writing them. Square root. This p hat is going to give me a minus h bar squared, nabla squared, plus m squared c to the 4th. Try that. Right? So now you can sit there as a theoretical physicist who's playing around with this, and you could say, there we go. Okay, I have a relativistic wave equation. It's this, right? So this is just a very simple thing to do, except this is no good for a few reasons. The first reason, it's really not great. I mean, it's okay. You could work with this, but it's not really great. The first reason is time and space are on different footings. What do I mean by that? I have an equation that's first order in time, right? This is del t, but second order in space. This is nabla squared, right? This is a second derivative. Now you might say, oh, why is that a problem? That doesn't sound like a problem. Well, first of all, let's just say from a symmetric point of view, just from mathematical symmetry, this is not desirable, right? We want time and space to be on equal footing. And on a more important note, this actually becomes very hard to solve precisely because these two derivatives are in different zones. That's the first problem with this. The second issue with this is if you expand the square root, and I'm not going to do it, it's a little trivial. If you expand the square root as a Taylor series in powers of these derivatives, you end up getting an infinite number of derivatives just because of the square root. So this equation is not really good. What does it mean to keep differentiating an equation over and over and over again? It doesn't really mean anything. You don't know. Well, first of all, psi of x, the bottom line, this equation is really cumbersome to work with, okay? So what did people do? They stared at it for a while and they said, oh, let's square it. Let's square it. So that's what they did, because they said, okay, that will make this a second derivative and it will get rid of the square root. So we'll be okay. So they literally squared it. Okay, and they got minus h bar squared d2 dt squared psi of x equals minus h bar squared nonless squared c squared plus m squared c to the fourth psi of x. Okay, and this was the first relativistic wave equation. This is called the Klein Gordon equation. This is also not great. I'll explain why. So it turns out this equation will be good for spin 0, for particles with no spin, which we'll talk about later. And it's better, right? Now I have symmetry here, right? So it's a little easier to work with. It's not terrible. And you can, we'll write this in a much nicer form, because what I'm going to show you is we're going to set h bar and c equal to 1, basically. So actually, let me write that up top. In QFT, we use natural units, quote unquote. That means h bar equals c equals 1. You can look up all of the units online and read about them. But if you see me getting rid of c's and h bars, just remember it's because we use natural units. Okay, I say that once and I'll never say it again. I probably will, but I, this is not the form we keep Klein Gordon in because of all the h bars and c's. Okay, so we've kind of succeeded. We're kind of getting somewhere. I mean, we're creating a relativistic equation, right? But now we should ask ourselves, what does it mean for an equation to be good in special relativity? And there's only one answer. It must be Lorenz invariant, right, guys? That is the fundamental question we need to ask ourselves. Is our equation Lorenz invariant? So how about we do that? How about we check if this is Lorenz invariant? And how about we create a more formal or a more rigorous definition of what we mean by Lorenz invariance? Because I kind of said that last time, but for special relativity, but we really didn't prove any of it. We really didn't show any of it. So let's do that now. So let's review some things in special relativity. So of course we have our 4-vector, right? That's our basic thing. That's the object we're going to work with. And we have our Minkowski metric. In QFT, we don't call the Minkowski metric eta. We call it G. Right? So G mu nu equals G upper mu nu equals -1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1. Right? That's our Minkowski metric. Okay, great. Now we're going to prove every single identity possible. So let's do it. So the first thing is, if I have this kind of 4-vector, I can get to another 4-vector by transforming it this way. Similarly, if I have an upper index, I can do it this way, right? So this is how I, basically what I'm saying here, oh no, this should be opposite, my mistake. Right, the metric raises and lowers indices, right? So these equations hold going from one 4-vector to another. I'm going to give a very fair warning. I'm going to write a lot of these kinds of 4-vector equations. It actually took me a little bit of time to realize that all of this actually works. So I'm going to spend some time, which no one does in college, they just write these down, and I'm going to show you that all of these equations actually work. Like, they actually work. They're not just random things I'm writing on the board. But let me just write them all down first. And of course, this one should be obvious. If you have this quantity, you get your Kronecker delta, right? If you're multiplying the metric twice, you'll get the Kronecker delta. which makes sense, right? Because you're only going to be multiplying the diagonals for this matrix multiplication. 1 times 1 is 1, right? Kronecker delta. And -1 times -1 is 1, right? So you get back the identity matrix, right? We saw that the Kronecker delta is defined as the identity matrix, right? 1s across the diagonal. Okay, so these are some of our basic properties of 4 vectors, right? The metric raises and lowers indices, right? And can take us from one 4 vector to another in a space. Any questions? Okay. Okay, that's all well and dandy. So let's go to our favorite object, which is what we really want to look at, the Lorenz transformation. So if I have x bar mu, I can go to another frame by a Lorenz transformation. And my Lorenz matrix for arbitrary transformations is a hyperbolic representation. So I have cosh phi minus sinh phi, 0, 0, minus sinh phi, cosh phi, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. Right, so that was our Lorenz transformation that we saw. Nothing, this should all be reviewed so far. I checked this time to make sure I got my koshes and all of that right. I know I get confused always. I have to remind myself. I can even write this really as this, x bar mu equals lambda mu nu x mu plus a mu, where a mu is some translation vector, translating it from one frame to another. This kind of transformation would be part of the Poincare group. So you can create equations that work and are invariant. And now we have some identities that we want to show. So the first one is this. I can go from one frame to another by utilizing my Lorenz transformation. Okay, well, shall we prove this? Shall we show? So basically in a usual QFT class, the professor writes this down and you go home and say, okay, what was going on? I'm going to show you that this works. Now, G mu nu and G rho sigma should be the same matrix, right? My Minkowski metric is not going to change, right? The indices are what we call dummy indices. They're just there as placeholders to tell you what's going on or to tell you how to contract and add. Can someone tell me what am I going to sum over in this matrix equation or in this tensor equation, really? What am I going to sum over? Am I going to sum over rho and sigma or mu and nu? So I'll answer it this time, and the next time we'll have someone. I'm going to sum over mu and nu because mu and nu are repeated in opposite positions. Remember? Rho and sigma are repeated, but they're all lowered. So in this equation, I'm not summing over rho and sigma. So rho and sigma have to stay fixed, and I'm going to sum over mu and nu. Now I know G mu nu and G rho sigma are diagonal, right? So they're only going to give me a non-zero contribution when the indices equal each other. So basically, I know that this equation, let's try it this way. Let's have rho equals sigma equals 0. How about that? And let's see if this equation holds. Then I'll get G 0, 0, lambda 0, 0, lambda 0, 0, plus, right, now I'm summing over. Now my mu's and nu's are going to change, right, because I'm summing over mu and nu. So this becomes G 1, 1, lambda 1, 0, lambda 1, 0, right? The rhos and sigma stay fixed, plus G 2, 2, lambda 2, 0, lambda 2, 0, plus G 3, 3, lambda 3, 0, lambda 3, 0 equals G 0, 0. Okay? G 0, 0, this component of G rho sigma, which is equal, they must be equal, right? That's what it means to be Lorenz invariant, right? The metric stays the same between frames or between transformations, right? That's what it means to be Lorenz invariant, that the metric does not change. So I should get -1. This thing should equal -1. So let's see. So G 0, 0 is what? G 0, 0 is -1. lambda 0, 0 is cosh phi. I get another cosh phi. Okay, plus G1, 1 is 1. Lambda 1, 0, rho 1, column 0 is minus sinh. I get another minus sinh. G2, 2 is 1, but lambda 2, 0 is 0. So this term disappears, right? Because lambda 2, 0 is rho 2, 0, 1, 2, rho 2, column 0, 0. And same thing here. So G3, 3 is 1, but lambda 3, 0 is 0. So this thing also disappears. So what am I left with? And this should all equal G0, 0. This should all equal minus 1. So I have minus cosh squared phi plus sinh squared phi equals minus 1, which is good because cosh squared phi minus sinh squared phi does equal minus 1. That's our identity because cosh squared phi plus sinh squared phi equals 1. Okay, so using our hyperbolic trig identities and literally just grinding through this and plugging it in, plug and chug, you get the right answer. Now you should try this calculation for rho equals sigma equals 1. You should just do that, right? Or you should try this calculation for rho equals sigma equals 2 and rho equals sigma equals 3. So just check if that holds. And this is a good exercise, right? Anytime I write this sort of equation, just check it. See what you're summing over, set some indices. You know what the Lorenz matrix is. Just use this one. This is the most general one, right? And just check it and see if it works. But isn't it so nice? You guys should really start appreciating this. You can write something so nice and beautiful, and it has all this information in it. It's just awesome. I love it. Okay, any questions, or can we move on? Okay, we'll move on. Is this confusing? Okay, it's basically like what we did last time, right? With the expanding the indices. That's why we did all of that. So I didn't have to do that today. Okay, excellent. Okay, great. Okay, and then we have our invariant quantity ds squared, right? That's our invariant quantity. Now ds squared can also be written as an interval, right? We said ds squared is less than 0 or greater than 1, right? We had intervals. So an interval is the distance between 2 points, x and x prime, or x minus x prime, right? That's what ds squared is. That quantity is called the space-time interval. We also know that the space-time interval must be invariant between frames. So let's show that. So our normal space-time interval can be written as x minus x prime squared equals g mu nu, x minus x prime mu, x minus x prime mu, right? That's our basic equation. This is basically just writing ds squared equals eta mu nu dx mu dx nu. That's what this is. Right? Except I'm writing each point as an interval, a space-time interval. Right, and I can always just write this as this thing, so the spatial parts. Right, I can always do that if I want. Minus the temporal parts. Right, so now if I go to another frame, x bar minus x bar prime squared, how can I go back to my original frame? What should I do? I'm going to need Lorenz transformations, okay? So I can write this as g mu nu, x bar minus x bar prime mu, x bar minus x bar prime mu. Now I can mitigate these by Lorenz transformations, g mu nu, lambda mu rho, lambda mu sigma, x bar minus x bar prime rho, x bar minus x bar prime sigma equals, well, this thing is just going to give me back a new matrix. So I get the new metric, G rho sigma. Wait, let me just make sure I'm doing this right. That contracts with that. Yeah, so these are going to be lowered. My mistake. G rho sigma x bar minus x bar prime rho x bar minus x bar prime sigma, right? And this is indeed equal to x minus x prime squared. So basically all I did here was I went back from one coordinate frame to another using Lorenz transformations. And hopefully as you keep doing this, you'll get used to seeing where the indices are, how to contract, how to not contract. If you have questions about that, come tomorrow. We can go slower. Okay. And what we're saying here is the physics needs to stay the same from frame to frame. So another easy way to say this is if I have a wave function psi of x, in my other frame, that wave function should also be the same. Should be psi bar of x bar. Okay, that's what I'm declaring here, just in one little statement. Anyone have questions about this, what I did here? Please ask, please ask. And of course, G rho sigma is equal to G mu nu, right? This is the same matrix. It's the same matrix, right? This thing is going to be basically rho and sigma. These two things individually could be different than mu and nu, but the square of them will give you the same scalar at the end of the day. Okay. And please let me know if I go fast, because I usually go fast when we do this kind of stuff, just because I've done it so much. Okay, so before we continue, I want to define a new quantity. So let's define this quantity d mu. Okay, and d mu is defined as this derivative, d dx mu, del x mu. And this is equal to 1 over c d dt and nabla. It's a space-time derivative. Similarly, if I have d mu upper, this is defined as the derivative of a 4-vector with a lower index. And all it does is it makes the time component minus. Okay? So I've defined two new quantities, space-time derivatives. We call these space-time derivatives. The reason we have this notation is because it's so nice and short, right? We don't have to write this whole thing out every time. We just write d mu lower, d mu upper. Please remember this because you'll be very confused. What are these d mu's? Remember, usually I get rid of the c. So just as a warning. Okay, so those are our space-time derivatives. They're very nice. And let's see. So now we know in Klein Gordon we have space-time derivatives. So let's prove some identities of space-time derivatives. First one, d mu x nu equals g mu nu. Okay, how is this possible? Okay, we know g mu nu is only going to be given a non-zero quantity when mu equals nu. So let's try this. So let's set mu equal to nu equal to 0. So this equation becomes d0 x0 equals g0, 0, right? What is d0? d0 is just d dt. x0 is what? x0 is minus t. Okay, let me explain something. So you're going to be saying, Kyle, what are you doing here? This is an upper index, and the time component should be minus, right? Right? And why didn't you put the minus here? But you put technically, and I was sloppy about this. When you have an upper index on a 4-vector, it gets rid of the minus sign in the time component. Okay, so technically, this thing is a column vector, and it gives you t, x, y, z. It gets rid of the minus sign. You know, usually we have the minus sign, right? But I'm sloppy about that, and a lot of people are. They just put the minus sign wherever they know it needs to show up. So I don't want you guys to be confused. So let's just do it the right way. So this would be a minus d dt, and this would be t. And this should equal -1. And it does, right? Because d dt of a constant t is just 1, and that's a minus sign. Right? So this works. Make sense? Let's do another one. Let's set mu equal to nu equal to 2. Right? Can someone tell me what this equation will give me when mu equals nu equals 2? Can someone work that out in a second? Anyone? You all know what G22 should be, right? So it's not a trick question. Rika, can you tell me? Maybe she's not there. Anyone? Jenna, can you tell me? You only have 2 options, right?
I'm gonna guess and say 0.
Okay, so let's work that out. That's okay. If I have G mu nu is what? -1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. What is G22? G22 is the second row and second column. The second row, this is the 0th row. This is the first row. This is the second row. Okay, so I'm in the second row. And the second column, 0th column, first column, second column. So this is the second column. So this is it. So it's 1. Right?
I didn't understand what you were asking. That was the only thing I knew that it was going to equal
Okay, so
1.
this is d2, right? So then my equation, so let's just work this out. So I have d mu x nu equals g mu nu, right? That's what I'm trying to show. Mu equals nu equals 2, right? So these indices are equal to 2. d2 x2 equals g22. We know that g22 is 1, right? d2 is just del del y, right? That's just part of our 4 vector, how we label them. And x2 is just y, right? In the 4 vector. We wrote it as a column. So the derivative of a constant is just 1. It's just the derivative of y is 1, right? Because if I had d dy of 2y, I would get 2, right? Those are our basic derivatives, right? If you have this derivative, you get back the coefficient. So that's it. So it works. Okay, if you have questions about that, ask me. So tomorrow, because I'm being really, really serious, because if this is confusing, you're going to be very lost come January, and that won't be fun. So please, please let me know. That's what I'm here for. Okay, let's prove another one. So if I have d bar mu, I can always transform again to another frame. This one you can do. I'm not going to do it. I'll do this one. And if I have this combination, d bar rho, d bar sigma, how can I get, oh, sorry, not d bar. X bar sigma, how can I get to the other frame? Let's see. So I'm going to need the Lorenz transformations. I have rho mu d mu times, I'm going to need another one, sigma nu x nu. Okay? Obviously, this derivative is acting on this 4 vector, right? That's what the definition. This is a derivative with respect to the 4 vector. So it's not acting on these guys. So I'm going to have to rearrange this. Rho mu, nu sigma, d mu, x nu, right? Because this is acting on this. That's the definition. This guy is what? G mu nu. Right? So this thing can be written as rho mu, sigma nu, g mu nu, and this is just g rho sigma. Okay? So it works. When I use Lorenz transformations, I get from some d bar frame, I get the same metric back. That's the key. The metric should stay invariant. Let's prove this, I guess. Let's prove that this thing, this equality equals this thing. Let's do that up here. You can already see, guys, that it's going to get more drawn out than quantum mechanics, right? Just because we have so many more things we need to work with, right? The indices are so important. Okay. So what do I have? I'll just rewrite it. D bar mu, X bar nu equals what? It equals lambda. Oh, I had this as a rho, right? Yeah, and a sigma. So this is rho mu d mu sigma nu x mu rho mu sigma nu d mu x mu equals rho mu sigma nu g mu nu equals g rho sigma. Again, these are dummy indices, right? I could call the sigmas chi, I could call the nus mu, it doesn't matter as long as they're all in the same spots. Okay, so I'll write down my Lorenz matrix again. Do we need it or do we remember it? I think we all have it written down, so I'm not going to rewrite it. Okay. So let's see if this works. Let's see if this thing equals this thing, right? So let's see if this quantity, lambda rho mu, lambda sigma nu, d mu, x nu, equals lambda rho mu, lambda sigma nu, g mu nu. Let's see. Okay, because that's what I'm saying here. And let's just even do this. Let's say they all equal rho sigma. Okay, let's see. Let's just write it out. Let's make one index. So rho and sigma are going to be the same. Look, in the whole equation, they've stayed in the same position. Isn't that amazing? They haven't moved. That means I'm not summing over them. I'm summing over mu's and nus. Look, see, that's the beauty of these equations. They're very symmetric. They're very beautiful to work with. I mean, once you get the hang of it, it's so easy. And it's awesome because it looks so complicated to the naked eye. But to the physicist, yeah, you just stare at it and you know. Okay, so let's make rho equals sigma equals 0. Let's do it. So 0, 0, I have to sum over that eventually. 0, 0, d0, x0. Plus, I'm going to write this whole piece first, okay? Plus 0, 1, 0, 1. d1 x1 plus 0, 2, 0, 2, d2 x2 plus 0, 3, 0, 3, d3 x3. That's this first piece. Equals, I'm going to do the same game here. 0, 0, 0, 0, g0, 0 plus lambda 0, 1, 0, 1, g 0, 1, oh no, g1, 1, sorry, plus lambda 0, 2, 0, 2, g 2, 2, plus lambda 0, 3, 0, 3, g 3, 3, equals g rho sigma, rho equals sigma equals g0, 0. Okay, that's that equation written out, right? Expanding each piece of the sum. Now it's a matter of plugging in. And of course, we should get a -1. All of this stuff should equal each other. It should all equal -1. Okay, I'm going to write that up top. We'll start writing this bad boy, this long thing. Like, are these equalities okay? Did I just make them up? So lambda 0, 0 is cosh phi. I have 2 of them. So I get cosh squared phi. D0 is it's d dt. I'm just going to make this positive and then make this negative. Is that okay? I'm just going to flip the signs because I don't Want to remember that. Lambda 0, 1 is what? Minus sinh. So I get 2 of them, so it's positive, right? So sinh squared phi. d1 is ddx on x. This is 0. This term is 0. Lambda 0, 2 is 0. Lambda 0, 3 is 0. Okay? And that equals what? Lambda 0, 0 again is cosh squared phi. You can see this is already starting to work. G00 is minus 1. This guy is minus sinh phi. Oh no, it's squared. So it's plus sinh squared phi. G11 is 1. This term is 0. This term is 0. This is just minus 1. And it works, right? So let's simplify this even more. Can I erase this guy?
Yeah.
Okay, good. And I know it's very long. Get used to it, guys. Get used to it. This is the beginning. This is the beginning. Okay, minus 1. ddt on minus t is minus 1. So I get cosh squared phi minus cosh squared phi from this derivative. This is just 1, right? Plus sinh squared phi, and you can see it worked out, right? Equals minus cosh squared phi plus sinh squared phi, right? Equals minus 1, and we use our identity. Cosh squared phi minus sinh squared phi equals cosh squared phi minus squared phi equals minus 1. Okay, it worked. So you should start to really appreciate this now, because usually people don't see it. They just see it and they go, oh, that must work. But hey, it actually does. It actually does. So I hope I've hammered in Lorenz invariance now in your head forever. And you should practice it a lot more. Okay, very good. So what happens to Klein Gordon? Okay, we're done. We're done with the detour. What happens to Klein Gordon? Let's take a look. So Klein Gordon becomes minus h bar squared c squared d naught squared using my new space-time derivative notation. Psi of x equals minus h bar squared c squared, nabla squared plus m squared c to the 4th psi of x. Let's see if this is Lorenz invariant. First I'll do some simplifying. So I'll write this d2 is equal to d mu, okay? And this is equal to minus d naught squared plus nabla squared, okay? I've just defined this like squaring my derivative operator. And so Klein Gordon becomes minus d naught squared plus m squared c squared. Let me do the algebra. Yeah, over h bar squared psi of x equals 0. This is Klein Gordon now. And in another frame, in another Lorenz frame, it would be minus d naught bar squared. Oh no, not d naught, d squared, sorry, right? Because we have to take care of this navla. Minus d bar squared plus m squared c squared over h bar squared. Psi bar of x bar equals 0. So these are my two frames, Klein Gordon. Okay, so this was just cleaning it up. This is just notation. And then this is my two equations. Now we want to check if these two things are equal. That's the point. That's what we want to do. I'll just write this in the way we usually write it, although I'm not going to work with it. Usually we set h bar equal to c equal to 1. And so Klein Gordon becomes minus d squared plus m squared psi equals 0. And usually d squared we write as box. So minus box squared plus m squared psi equals 0. In case you see this online, box is called the D'Alembert operator, where it's like the gradient. So I guess the next step up from a triangle is a square. I don't know, where you have minus d2 dt squared, d2 dx squared, d2 dy squared, d2 dz squared. It's just like the gradient except with second derivatives. Okay, I guess 4 sides is 1 bigger than 3, so it works. So you can see that this is Klein Gordon. It's equivalent to this. This is Klein Gordon. It just people write it in different ways. I don't want you to get confused over that trivial thing. Okay, folks. Deep breath. Shall we check if Klein Gordon is Lorenz invariant? It's not that hard, actually. Let's check. So the question is Klein Gordon Lorenz invariant? Okay. So the first thing we do is we set psi of x equal to psi bar of x, right? Psi of x, psi bar of x bar, right? So we don't have to worry about these two guys. That's like an implicit assumption that they must be equal at that point or whatever. So all we need to check is if I have a square on my derivative, right? That's really what's changing here. Is it Lorenz invariant? These guys are constants, so obviously it doesn't matter, right? What frame you're in. So as long as these two things are the same, I can transform between them. I'm fine. Klein Gordon's Lorenz invariant. So let's figure that out. Very good. Right? So I need to check if d bar squared equals d squared. That's the whole point. So d bar squared equals g mu nu. D bar mu, if I'm yeah, it's got to be a d bar. I don't have Lorenz transformation. D bar mu. You guys are all really smart, so you know I'm going to bring Lorenz transformations in. That's what we do. G mu nu, mu rho, mu sigma, d rho, d sigma, and this is it. This is equal to d squared, right? Because this will give me my new, I'll just write this. This is equal to g rho sigma, this quantity, right? Which we've defined many times, right? And so you get g rho sigma, d rho, d sigma, which is d squared. So it is, it works. You might say, oh, that's pretty trivial, big deal. It's not, right? Because what if I had in my Klein Gordon d cubed? Would that be Lorenz invariant? No, I mean, how would you contract that? I don't know. How would you transform, right? Like if this was in Klein Gordon, I don't know how this would be consistent with special relativity, right? Or if I had like d over, that would work. That would work, but like something like that wouldn't work, right? Or how about just d? Right, like how about I just said d plus m squared c squared? This might be an interesting research project, right? Coming up with new equations and seeing if they're Lorenz invariant or testing these ideas. Cool? Do we understand what I did there to show it's Lorenz invariant? Okay, I hope so. That was the whole point of all of this. Now, it turns out Klein Gordon has a huge problem. Now, it's a pretty big problem. Here's the thing. We use Klein Gordon a lot, actually. I think the first whole month of quantum field theory, we're going to use Klein Gordon. It works for equations for particles that are spin zero, that have no spin. Wow, it's 10:30. Wow, I had so much more to do, but I'm not going to do it because I didn't realize how much time this was going to take, which is fine. I hope your Lagrangian mechanics is okay, because we're going to do a lot of it next time in January. All we'll do is Lagrangian mechanics. Okay. What's the issue here? So how about we take a 5-minute break and I'll show you what the issue is, because now I just want to get through these basic things. Okay, so let's take what time is it actually? Let's come back at 32. Okay? Get a stretch break. But this is really only for Jenna, honestly, just because she wakes up early. If it wasn't for Jenna, guys, we would be going straight through. I'm not a big fan of breaks, but. Jenna, I hope this isn't too heavy.
No, it's okay. I understand the thing I missed about the thing I missed. I don't know what to call it.
Don't worry.
Yeah. I just got confused by when you did like the del instead of just like G.
Yeah. See, but it took us a long time to build the machinery to get here, right? It took like a whole.
Yeah.
The way it works, yeah. Are you still doing the open courseware class?
No, I didn't do the open courseware. I've been doing I finished like Calculus AB on Khan Academy. So yeah, that's where I'm at.
It's probably helping you with what we're
doing.
Because
a lot.
I mean, adding multiple variables in calculus is not a big deal. It's a little trivial, right? It's the same thing as single variable. You just have to be a little careful with how you organize things, that's all. Rika, how are you? I don't know if she's there.
I'm good. How are you?
Good? All right, good. Have you guys submitted your college apps yet? Early decisions?
I didn't do early decision, but I have a lot to do regular.
Yeah. No, that's probably a good idea. I just did early action. What do they call it? Single choice early action, or whatever it was called.
Oh yeah, restrictive early action.
Yeah.
Also, can you post the lectures from November 7th and the 15th?
Yes. I thought it went through, and then YouTube said, oh, this didn't upload. So yeah, I'll do that.
Okay.
Yes. I think people know the special relativity stuff is super important now, right? Because yeah. I had planned to do it over the winter, but I figured, hey, we have time. Let me just do it now. Okay. Oh my gosh, I really overdid it. I thought I'd have time to do like way more. That always happens. It's not worth it though, because that stuff is really like not so important.
I have a quick question.
Yeah, sure.
So for the cos squared, like in sine or sin square phi, what was the identity again?
Oh, it was cos squared phi plus sin squared phi is -1.
Okay.
Yeah.
Thank you.
Cos squared phi minus sin squared phi is 1.
Okay.
Yeah, the hyperbolic identities are weird, but very important to learn. Because guys, remember, that's what a Lorenz transformation is. It's a hyperbolic, right? Depending on how much the coordinates change, that tells you the angle at which the primed axes are going to shrink or move apart. So that's all that is. It's actually a very beautiful geometric picture, if you think about it. We're working on this space-time space, and we're just moving coordinates along it with these Lorenz transformations. It's really not crazy stuff. Groundbreaking stuff. Okay, let's begin. Let's continue. Okay, so what is the problem with Klein Gordon? So we know it's Lorentz invariant. And we're going to use it a lot, actually, for spin zero, for bosons. That's what we use, Klein Gordon. The problem is it is not consistent with quantum mechanics totally. So we know from quantum mechanics that this thing is the inner product of states, right? That's just the inner product. And I can write this inner product simply as the integral of, oh God, what am I doing? Of psi t, inserting a complete set of position states, right? And then this is just the integral. Psi star psi, right? That's the inner product. That's the probability amplitude. This thing is not time independent. This is dependent on time, this quantity. Yeah, it depends. The bottom line is it turns out in Klein Gordon, probability is not conserved. I'll explain why. You can look up more detailed explanations, and we'll go through this more, obviously, when we start real QM. But the problem with Klein Gordon is if you work it all out, you get different probability amplitudes from frame to frame. So it works in special relativity, and we'll use it a lot, actually, because you'll see we're going to change fundamentally what we're working with. Because if you're working with wave functions, Klein Gordon has issues. But if you're not working with wave functions, if you're working with some other fundamental object that's more fundamental than the wave function, then it works. And what is that fundamental object? It's a field, okay, which we're going to get to, that changing. Okay, so this guy Dirac, who is a really smart dude, said, let me try and fix this. Let me say that, and this is not going to make any sense right now. I just want to show it to you. Let me make my wave function psi sub a of x, right? Where a is just some discrete label 1 or 2. And he said, this is my new wave function, and these 1 or 2 indices, these a's, represent different spins. Okay, then he writes down this kind of equation, IH bar d dt psi a of x equals what? Equals minus IH bar C alpha j. You're going to say, what is that? I'll tell you. AB dj plus, yeah, MC squared beta AB psi b of x. This is called the Dirac equation. We'll also write this in a nicer form. And basically, this was his solution to adding spin. These two things will be matrices. Don't worry, none of this should make sense. Lorenz invariant stuff should, not this. This is just showing you where we're going to go. So basically, Klein Gordon works, but not for wave functions. It works for fields. And it works for spin zero fields. Okay? Where it works with bosons. Don't even worry about this. I just so you see it. So we need to confront a reality here. We need to confront the big problem. Basically, we're running into problems from this angle, from that angle. It's not working. We need to put space and time on the same footing in some sense, right? In quantum mechanics, we have a very important postulate, right? All observables are eigenvalues, right, of Hermitian operators. Right? All observables are eigenvalues of Hermitian operators, except one, time. Time has no eigenvalue, it has no operator. If you work in the Heisenberg picture, well, then time involves the states in the operators, right? E to the IHT, those are Heisenberg operators. If you're working in the Schrodinger picture, the states evolve with time, not the operators, right? But time itself has no eigenvalue. And this is a problem because in special relativity, time is a big deal, as we know, right? Time is not like some random thing that evolves states. Time is like a quantity now between frames, right? It's not like a set thing. We need to reconcile this. So we have two options, right, at this stage. The first option is, so option A, make time an operator. So promote time, I'll rewrite this, I'll say it this way, promote time to an operator. Okay, this could work, right? Then space and time are the same, they're on equal footing. And people have done this. You can look up Jeffrey Chew's Bootstrap. There are many, Jeffrey Chew, I'm talking about like the 40s. So I'm not talking about modern physics, but people tried this. It works, but it's very complicated. It's very annoying. It's like not even worth it. Option B, which is what we do, demote. So here we could make something an operator, right? To have some x mu of tau, right? That would be the idea in option A. And have it as an operator. Parameterize everything by tau and do it that way. In fact, actually string theory does this. String theory starts with x mu of tau and then adds more degrees of freedom. It adds a sigma. So this is a theory that does it this way, string theory. In fact, string theory is not a quantum field theory, actually. Okay. Or we could demote all observables to labels instead of operators, and labels of space and time. And those labels tell us about the dynamics at some point in space and time. That's what we do. That's what we do. So now our operators of quantum mechanics become labels, x and t, instead of x hat, or p and t, or p mu and x mu, right? And that's where we get our quantum field. So the most basic quantum field is this thing phi of x. Phi is what we call a scalar field. I think I've shown you phi. Scalar meaning spin zero. Scalar meaning spin zero. Okay, its equation of motion is the Klein Gordon equation. It will have a Lagrangian, right, from which we can derive that equation of motion, which we'll do. It will have an action, right? So now we're going to start building the machinery. We can describe the dynamics. Okay, so now we have our notion. So now what has happened is super important. Now we have changed the fundamental object from a wave function or a particle to a field. Okay, it's a super important switch. And that wasn't inherently obvious. I think Bob and I had a good conversation a couple Sundays ago about what actually a field is. And it's a very abstract idea, even though we talked about it for like an hour. I mean, it's abstract. It's not easy to pin down, but the thing to know now is we've changed what we're working with. Okay, very important. Okay, so if I want to evolve this thing, I can evolve it. I can evolve it still in the Heisenberg picture. It's not like I can't. Right, I can evolve it. Right, I mean, it's not really a big deal. So now let's try, and this will be our final exercise for today. And so the big takeaways of today are Lorenz invariance. We've changed the big quantity. We'll go through them at the end, the big takeaways. Let's write down a multi-particle Schrodinger equation. Let's just write one down. Not even care about relativity. We have IH bar dVt on psi equals some sum j equals 1 to n minus h bar squared over 2m. Now navla j squared. Now I have many particles. That's what I'm adding. Plus some potential plus u of xj for the Hamiltonian, right? Plus j minus 1 to n, j equals 1 to j minus 1, v of xj minus xk. I'll tell you what that is. All acting on psi. So I've written some multi-particle Schrodinger equation. This whole thing is my Hamiltonian. This is my total energy, right? This is straightforward. It's multi-particle, right? Because now I have a sum over each particle, right? From j equals 1 to n. And this is some interaction, potential. They're interacting here, right? Because when xj equals xk, you get a contribution here. So this is some interaction between them. So this is some model of a multi-particle Schrodinger equation, right? This is something that could work. And of course, psi is like now labeled. Sorry, psi is like labeled at multiple positions, right? And now I want to solve this thing by introducing a field, A of x, and its Hermitian conjugate, A dagger of x. Ooh, okay, we're starting to see shades of the harmonic oscillator. And again, this part's not going to make too much sense yet either. But and I want to say they obey commutation relations, like our operators of the harmonic oscillator. So I have A of x prime, commutator equals 0. A dagger of x prime equals 0. A of x, A dagger of x prime equals delta 3 x minus x prime. So this should be really familiar. These are basically the commutation relations of the harmonic oscillator, except now we have a delta function here instead of, what was the commutator in quantum mechanics? I forget. But these two are still 0, right? And this gave some contribution. And this is equivalent to the harmonic oscillator and its raising and lowering operators, A plus and A minus. Okay. So I can rewrite this Hamiltonian now as a continuous object that is defined as some kind of superposition of these fields. Again, I'm going to try and explain this, but we're going to need more machinery. But I want you to see it, and it should make some sense. So now my Hamiltonian for multi-particles, this is discrete, right? Is d3x, this is the Hamiltonian we'll work with, a dagger of x minus h bar squared over 2m nabla squared plus u of x, A of x plus 1/2 integral d3x d3y v of x minus y, A dagger of x, A dagger of y, A of x, A of y. You're like, what is this Hamiltonian? What is even going on here? Okay, let me explain. We have a very interesting thing going on. I've introduced fields. Those fields are going to be labeled at each point in space and time. Okay. They're going to have wave functions at each point in space and time. They're going to have descriptions at each point in space and time. My operators have become labels. And I've written my Hamiltonian somehow as a combination of these fields, A and A dagger. And this Hamiltonian is going to act on the field, right? That's the idea. Now the Hamiltonian is acting on phi. Okay. So the way we're going to construct this, so in quantum mechanics, the raising and lowering operators took us up energy eigenvalues, right? They took us up and down energy eigenvalues. In quantum field theory, these operators are now called creation and annihilation operators. They're analogs to the raising and lowering operators. So A dagger of X is a creation operator. A of X is an annihilation operator. Annihilation. And when they act on a state, they either yield a particle or destroy a particle. So A dagger acting on this state called the vacuum, when I have 0 here, I mean nothing, empty, the vacuum state, gives me back one particle with momentum k. So I can write A1 of k. I get back one particle with momentum k. Similarly, A of X acting on the vacuum gives me 0, doesn't create anything. It just destroys. So the way we're going to, instead of taking the up and down energy eigenvalues and eigenstates, now these operators are going to create and destroy particles with some momentum and some label. Okay? That's how we're going to construct these objects. Okay, so we're starting to develop the machinery. Of course, all of this is not going to make total sense yet. That's okay. Just know that now we are changing sort of how we're going to work with these constructions. Okay, great. So what are the big takeaways and what should we look forward to? The first big takeaway is we are now working with a new fundamental object, the field, right? Where operators have now become labels in space and time. The second fundamental idea is in order to create a theory that is consistent with relativity, we need Lorenz invariance. Okay. By the way, just think about it if you were an experimental physicist and you're looking in the lab. Like these things have actual consequences, right? You want Lorenz invariance with your numbers or your frame or the way you're designing your physics. So you don't waste a ton of money. Okay. Okay. Now, what is the program? The program is we're going to start with a Lagrangian for any theory in quantum field theory. We're going to have a Lagrangian and we're going to derive equations of motion, right? And we have seen that with any action, you can get equations of motion. Now, what are we building up to? We're building up to a description of the standard model. The standard model is our model of elementary particles. It describes all the fundamental forces. There are 4 fundamental forces: electricity and magnetism, the strong nuclear force, the weak nuclear force, and gravity. The strong nuclear force is what keeps the nucleus together. It's why we're all walking around, okay? Because you have protons, no, sorry, you have a proton and you have an electron rotating around it. They should attract and you shouldn't be here, but that doesn't happen. And the strong force binds the nucleus together. It binds the proton together. The other nuclear force is the weak force. The weak force is responsible for decays, neutron decay, beta decay, various other kinds of processes. And then gravity we're not going to talk about here because we have no quantum theory of gravity. That's the big story. You all know this. I've mentioned it before. Quantum gravity is a big mystery. Maybe one of you will solve it. Maybe we'll solve it together. Who knows? But that's the big problem. And so the standard model is what we call a gauge theory, non-abelian gauge theory in its entirety, except for quantum electrodynamics is actually abelian. You'll see why. And it's made up of groups. You can actually describe the whole standard model in the language of group theory. The three groups we'll use are SU3, SU2, and U1. So your group theory language is going to be important. Okay, great. We're going to be trying to figure out, a big part of field theory will be trying to figure out scattering amplitudes, right? So we're going to look at particles scattering off each other and we want to see what happens. What's the lifetime of the particle? What's the decay rate? How do they scatter? What's the amplitude? What's the likelihood of this process happening versus this one? And we're going to derive these things called Feynman diagrams, which we've kind of described already. We're going to figure out how to compute amplitudes from them. It's not that hard, actually, which is pretty phenomenal. You'll get to the point where you look at a Feynman diagram and you can say the amplitude. You don't even have to compute anything because there's the rules that Feynman came up with, which were so revolutionary. In fact, Schrodinger said that Feynman brought quantum field theory to the masses. And he was kind of right. I mean, anyone can compute. I can teach a high schooler how to compute. Well, you guys are high schoolers, but you're not ordinary. I can teach ordinary high schoolers how to compute a Feynman amplitude. So it's not a big deal. Okay, any questions? We have a few minutes before Gabe gets here. So if you have questions about the paper, I can answer them. If you have a topic you have in mind, I can answer them. And remember, the presentations next week will be round 1 of presentations. So once I get all of your topics, I will assign who's going next week and who's going week 2. You might all go next week. So I don't know if we don't have enough people.
How are the presentations gonna go?
Yeah, so I don't know yet because I don't know how many of you are going to do it in terms of timing and stuff. But you guys can make a PowerPoint, right? And show slides. You guys can make and you should submit your paper to me before the presentation. It could be like a minute before, it doesn't have to be like a few days before. You can do what Gabe does if you have access to that with the pen on Microsoft or whatever, or tab, I don't know. You can, if you have a board or a whiteboard, you can find, I don't know, you can do it any way you want. And then everyone here who comes to the presentations or who is presenting needs to ask one question to the presenter. That's the rule we're going to have because I want some discussion. You can certainly ask more than that, but that will be the rule. So you come ready and listening and have stuff prepped. So yeah, Monster, I'm not sure. I'll send the specifics of that. I'll send the specifics of that tonight when I get your topics.
Okay.
Okay. I'm here until Gabe gets here. So if you have anything else, please let me know.
I have a question about nuclear force. Like
About what? Sorry?
about strong nuclear force.
Strong nuclear force.
So how would the properties of quantum mechanics change if it didn't exist? Because they would be, the protons and electrons would just attract then.
Yes. Yes, so actually let me rephrase that. The strong, sorry, I should have been more clear. The strong nuclear force is only responsible for holding the proton together. It doesn't have anything to do with the electron moving around the proton. Sorry, thank you for bringing that up. The fact that the proton doesn't crash into the nucleus, crash into the proton, has to do with quantum mechanics. It has to do with wave-particle duality. That the electron is not just a charged particle, and the proton is not just a charged particle. If you describe them as wave functions, well, then the charge is out the window, right? Now you're looking at a different object. And you can look this up. Why doesn't the electron crash into the proton? That might be a good topic. But it does have to do with the weirdness of quantum mechanics. Yeah, but is that clear, Mansoor? The strong nuclear force is not responsible for that phenomenon.
Yeah, that's clear.
Okay, you guys have heard of quarks, right?
Yeah.
So quarks behave with the strong interaction. That's the whole theory of quarks. And you might have heard of up, down, strain, charm, top, bottom, or whatever. There's some famous song about this. Someone told me once. So those are the flavors. So that's, we got very creative with naming things. So we have flavors of quarks. And actually, one of the topics we'll do is flavor dynamics. It's pretty cool. So. Oh, we've never finished early before. This is so weird. How about you guys, Artem and Serafina? How are you guys feeling? Because I haven't heard much from you guys. I think you guys joined in a little later in the course, maybe midway. I don't know if either of them are.
Yeah, I think
Yeah,
I have some catching up to do.
okay. It's interesting because a lot of the folks who started, a few of the folks, not a lot, are doing this asynchronously now. If you guys remember Kelly, or if you remember a few of the other people, so we're all on different pages. Good. It's okay. I think next time we'll do string theory. That's what we'll do. But if I do recall, if someone can remind me, on one of the problem sets, you did have to work with Lorenz transformations, right? Hi, Gabe. What's up?
Not much. How are you?
I'm doing good. I'm doing good. We just went through all of string theory in 40 minutes, so
Oh, that's wonderful.
I'm just joking. We have we've introduced the creation annihilation operators now.
Ooh, nice. So
We're
we're
starting-
QFT.
Yes, we're starting to build up QFT, which should be good. Okay, folks, so your paper topics are here tonight. I'm very excited because it's Gabe's final problem solving session until January. So Gabe is probably happy about that.
It's, I'll miss you guys, but it's nice to have a break. I'm not going to lie.
Yeah, just a nice 1 month retreat. And then we'll come back and knock out QFT in a few months too. So again, I look forward to reading your topics. They don't have to be very solid. And once I get all of that, I will send everyone a description of presentations and how that will work next week and maybe the week after. Okay, folks, thanks a lot. See you tomorrow morning, those of you that have questions. And Gabe, take over, talk about 4 vectors and matrix inversions.
Mm-hmm. Okay, let's do it. Oh, Kyle, don't forget to make me the host.